Hi. What does actually have process vessels and fuel cells to do with each other? And how can we, say, increase the efficiency of a fuel cell by using that? Stay tuned. So, in principle, we are figuring out how to increase the efficiency of a fuel cell system. What is happening in a fuel cell actually? Actually, it's cold combustion we're talking about. In a fuel cell, at the ion exchange membrane, we have combustion of hydrogen and oxygen. In principle, burning fuel and burning air. So at the burning air side, we certainly have also the production of water itself. At the fuel side, we are usually using dry components, but experimental results showed that it makes a difference if you're using a dry hydrogen flow or something which is enriched with a certain amount of water. But what's the optimum point here? So in order to find that out, we would need to incorporate such a process vessel as that here, called bubbler. You probably remember one of our other videos where we were talking about that in principle with bubbles created in a glass of water. This is exactly more or less what's happening in here as well. So you basically have an inlet, you have a dip tube into a liquid, and you have an outlet. And in between, you create bubbles in the liquid. And what you need to take into account is your total experimental setup here. So we would have a certain operation temperature range that we would need to consider. And in this case, we deem to have a water concentration in the hydrogen burning gas of roughly to 42 hectopascal. This is created using a water temperature, considering the equation of Clausius-Clapeyron, of roughly 30 C. So that's roughly our temperature range that we are considering. But what are the other parameters? We are using a general pressure at ambient conditions, so 1013 hectopascal. We are figuring a experimental duration of roughly 5 to 6 hours, and also a pressure according to ambient conditions. I mentioned that. So, but what is happening? So we enrich the hydrogen flow in the vessel, and what is happening then? We roughly have to consider that we have a distance of the enrichment vessel to the fuel cell of, let's say, 4 to 5 meters. And what is happening there? The temperature in my laboratory is roughly 20 C. So also my line from the process vessel to the fuel cell is roughly 20 C. So what is happening in the line then? Certainly you have condensation in there. And that's creating a system which is more or less supplying unpredictable conditions in there. So what you would need to do is you would need to heat up your whole line, your whole gas line system in your laboratory. Certainly above 30 C, you can tune it up to 100 C, for example. That doesn't matter too much, at least as it's above 30. So that's how you solved your challenge, let's say, from the vessel to the fuel cell. But what is happening in the vessel itself? Let's say we are putting it on a table and leaving it up there, let it run. So what we certainly take out of the vessel is energy, because we are evaporating water. And that's quite a lot of energy that we take out of it. So what is happening in there? What is happening is that we cool it down. That's certainly something that we don't want, because that's lowering the temperature, and in return it's lowering the vapor pressure of the water. Means during the duration of 5 to 6 hours it certainly matters a lot, and we have again results that we cannot predict. So what you would need to do is you need to temperature control, let's say heat up the vessel. That can be done by different methods, but that's a detail I would like to talk about with you in a later session. So you see that you need to really make up your mind on the process parameters such as temperature, line system, design of the vessel itself for a pretty actual simple system such as water enrichment of a carrier gas stream. That's what I'd like to bring closer to you in this video here, and I would certainly be happy to talk with you about your challenges in a different session or at a later stage. Take care and stay healthy.